This is Phil Koopman with a talk on embodied AI safety. Embodied AI safety involves what used to be called embedded systems, which is a computer that has sensors and actuators, combined with AI, artificial intelligence based on machine learning. This is not a small change involving just adding a little feature capability, but rather a profound transformation of what it means to do safety. This talk will go over why that is. To be proficient in embodied AI safety, you need to know 4 areas to the level of at least literacy. One is system safety, another is cybersecurity, a third is AI-based machine learning, and the fourth is human-computer interaction. If you're missing one of these 4 areas, expect to have trouble trying to do embodied AI safety. In this talk, we'll go on a journey to understand embodied AI safety, starting with a survey of the implications of the 4 core areas, followed by revisiting what acceptable risk means in an embodied AI system, talking about embodied AI challenges, and ending up with a reimagining of what safety engineering means when you add machine learning-based AI. The motivation for embodied AI safety is important to start with. Here's a cute little robot, and the robot's been around for a long time, but robots have had issues with some core capabilities that until now have been very difficult to pull off. The first is perception tasks. Deciding that an object is a person or something else is really hard to do, but machine learning does a pretty good job at that. Natural language interface is another capability that's really nice to have, and again, machine learning gets us most of the way there. And finally, dealing with an unstructured open world environment is an important robotic capability. All 3 of these capabilities are currently done using machine learning. But the problem is that machine learning is not something that traditional approaches to safety have been able to cope with. Now, we care about safety. I mean, here's a robot, and if it's a little toy robot, maybe it's okay. But give that robot a hammer and tell it to start beating on things because you want it to be useful, you want it to hammer nails in or something like that, gives it a way to do some potentially significant damage. So once you're interacting with the physical world and trying to make changes to that physical world, you have to think about the safety implications of taking those actions. And you start asking questions like, how safe is safe enough exactly? Nothing in this world is perfect, but it needs to be acceptably safe, whatever acceptably means. And where's the accountability for harm? If something does go wrong, where's the accountability? I can assure you that robot does not care if it gets locked up in jail for using the hammer to harm someone. So how exactly does that work? When something goes wrong, who's accountable, and how do we make sure there's an incentive to not let things go wrong in the first place? And how do we instill trust in the technology? If you have technology that has questionable accountability and can do damage, why should people trust it? How does that work? So those are all topics we'll cover in this talk. Computers are not necessarily safer. Let's just start right there. Just because you have a computer does not guarantee safety. Now, people love to say that human operators make mistakes. For example, in self-driving cars, one of the rationales for them is that humans drive drunk and they drive distracted. And absolutely, humans are fallible. They're not perfect. But it turns out computers make mistakes too. So saying that humans make mistakes does not necessarily mean computers will be better. They might be better, they might be the same, they might be worse. And we have to keep that in mind when we're talking about safety. Now, here are 2 examples. The first is a robotaxi that crashed into a utility pole. There's a long, detailed explanation, but the short version was that it knew not to crash into curbs, but it did not know not to crash into utility poles. And until that mishap, which happened millions of miles into operation, it had not had the chance to encounter a utility pole that was not also protected by a curb. Surprise! Turns out software has defects too. Even though it doesn't drive drunk, even though it doesn't drive distracted, it can still have mishaps. Now, if you look at that, if I had told you it was a human driver, you would have said, oh, that human driver was probably texting. Well, robotaxi wasn't texting. It just had a problem with its software. Here's another example. A robotaxi from a different manufacturer crashed into the back of a bus. It had lidars, it had cameras, it absolutely had the ability to detect the bus, and the lidars did detect the bus. But the problem was that it had been trained that buses are about 40 feet long, and this was a 60-foot bus, one of the ones with the joints in the middle. And it looked at the front of the bus, measured 40 feet back, and said, well, I know how long the bus is, so I'm going to drive, assuming it's a 40-foot bus. The LiDAR apparently saw the back of the bus, but it decided to ignore it because it knew how long buses were. Again, a software defect. So robotaxis and computers don't make human mistakes, but they make mistakes that look like human mistakes for entirely different reasons. Just because it's a computer does not mean it's guaranteed to be safe. It will fail for different reasons, and safety has to do with making sure that the computers fail infrequently enough and in ways that we can tolerate, which is what embodied AI safety is about. Let's dive into the 4 core areas. The first one is safety engineering. The thing about safety engineering is it's all about risk mitigation. You identify some hazards and some risks, and you mitigate them, and you make sure that the mitigation actually works. Here's a picture of someone out on a rope having some fun, and you can say, well, what's the hazard? Well, the hazard is they might lose their grip or somehow slide off the rope and fall down. And if you look closely, you can see there's a little hasp attached to a lanyard so that if this person falls off the rope, that will keep them on the rope so they don't plunge down to the bottom of the ravine. There's some technical areas with safety engineering, whether it's computers or anything else. One of the things you do is redundancy to help mitigate failures. If you look really closely at this picture, there's actually 2 ropes. So if one breaks, let's hope that the other one's strong enough to hold that person up. There's safety standards for engineering rigor. There are a bunch of safety standards associated with this equipment, making sure, for example, that the rope is manufactured and tested in a consistent way so that you know the rope is strong enough. And there's some design assurance beyond just testing. So you don't just say, well, let's see how strong the rope is by pulling on it. You make sure that there are standards for construction and quality control for all the equipment. That applies to ropes. It applies to computers. That's just how safety engineering works. There's a strong need for safety culture and independent oversight for safety. You can have all the standards you want, but if people do not take them seriously, you're not going to get safety out the other end. What I'd like to do now is dive a little bit deeper into safety engineering before we move on to the next topic. A core activity in safety engineering is risk analysis. You list all the possible hazards. The person could fall off a rope. A car could steer incorrectly into an obstacle and have a crash. A drone could fly into an airport restriction area, and so on. You identify all the hazards, you determine a risk for them. The classical risk equation is risk is frequency times severity. Now this works for many risks, but it has some problems with extreme risks, which is what we care the most about for safety. You can take a mathematical approach to this, but we're going to use a simplification that is commonly found in safety standards. It's a thing called a risk table. This is a very simplistic example that has a 2-dimensional table. One dimension is severity. You can have low severity or high severity of a hazard, and you can have low frequency or high frequency of that hazard. So how often does the hazard manifest as an issue, and how severe is the loss event if the hazard results in a loss event? If it's high frequency and high severity, we say it's high risk. Low gives you low risk, and low severity, high frequency usually gives you medium risk. Now, one of the hardest things in safety engineering is dealing with low frequency, high severity. It's a little tricky how to assign a risk there. We're going to come back to that. But given that you've figured out all the squares in this table, and there might be 5 rows and 5 columns to give you more granularity, but ultimately you get a bunch of risks that range from low to high. And the approach to safety is you assign a safety integrity level or something similar, where you say, well, a low safety integrity level needs a little bit of engineering rigor, and a high safety integrity level is associated with high risk, requires a lot of engineering rigor, and probably requires a lot of resources such as redundancy. And when I say engineering rigor, that sounds pretty abstract. So here's a concrete example. A typical safety standard, regardless of what domain it is, it might be aviation, it might be rail, it might be petrochemical, it could be whatever, they end up usually having a set of tables saying these are the practices you need to follow. So if you have SIL 1, which is the low level of engineering rigor, low level integrity, it may say there's a couple techniques you have to use, but don't worry about the rest. I put in some usual suspects. The specifics here aren't important, but rather the trend is what's important. For SIL 2, which is a little medium-low risk or medium risk, There's more engineering analysis required and more runtime activities and more structural activities required. As the SILs increase, maybe there's some informal things you're no longer allowed to do and you have to switch over to more formality. And at the highest level of risk, you generally have to do everything except the stuff that is deemed inappropriate because it's too informal. The idea of doing this is that if you have high risk, you can use a high SIL, and that gives you a good expectation of safety. One of the core problems for safety for embodied AI is that we're still figuring out what these tables should look like for embodied AI. So if you go to a safety standard, there are some emerging standards that tell you some good practices, but we do not have what we have in conventional software, which is tables that have been around for years or decades that say, here are the activities you do, and if you do these activities and you do it with good safety culture and independent oversight, you can expect a good safety outcome. That is still immature for embodied AI, so that's a major safety challenge. There are some higher level safety engineering challenges which have to do with understanding the difference between, yeah, it kind of seems to work, and no, really, this will be safe at scale. The first one is that you have to understand only the bad days matter. Let me make that really concrete with a hypothetical example. Let's say that you have 99,999,999 safe miles out of 100 million. Now in the US, it's ballpark 1 fatality per 100 million miles, depending on the year, depending on a lot of specifics, but it's about 1 fatality per 100 million miles, which means all but one of those 100 million miles was a safe mile. Nobody died. Sure, there can be other crashes. Let's set that aside. Let's say you have that ending in 999 versus that ending in 998. Well, those numbers look almost the same. And so if you're saying, well, we're worried about it performing well, those numbers are basically the same. But safety can't look at it that way. Safety has to look at, well, you had 1 fatality per 100 million miles. We had 2 fatalities per 100 million miles. That's a factor of 2 safety difference. So the thing is that only the bad things matter for safety because you're expected to almost never have a fatality. So a number that seems almost the same with a very small change can actually be a dramatic change in unsafe miles, which are the things that matter. In this context, a single 10-mile safe drive means essentially nothing. Oh, I drove 10 miles and everything was perfect, must be safe. Well, 99,999,990 miles to go, and even then your confidence is kind of low. The second big problem with safety engineering is that because rare high severity events dominate the safety discussion, you have this struggle with zero probability times infinite cost. If something almost never happens, well, 1 per 100 million is almost never, it's very rare, but it does happen. What if you have near zero probability and a catastrophic consequence? Remember the question marks I put in low frequency, high severity? Well, what do you do with that box? Economics pressures you to say, well, it's never going to happen, so we're going to assign it a low SIL because there's less engineering rigor, less redundancy, it's a cheaper product to make, easier to make. So it's probably not going to happen, so we're not going to worry about safety. Economics pushes you that way. News headlines push you the other way, because once the bad thing happens, you say, wait a minute, that horrible thing happened. We should have guarded against it, even though it was extremely rare. What you see is these philosophy for rare high severity events varies depending on the application domain. Automotive tends to make these rare high severity events low risk, low SIL, and aerospace tends to make them high SIL. In the robotaxi business, there's a lot of incentive to not worry about rare events. In fact, companies will say, well, that's a rare event, so it shouldn't count. And that works until the company has a really severe event that makes the news and causes lots of confidence. And ultimately, many companies have been put out of business by having a single high severity event. One of them was Cruise, which went out of the robotaxi business after they dragged a pedestrian down the road. And of note here is that it was a horrific crash, but it was a severe injury. It was not a fatality. And yet that and some associated circumstances were enough to take them off the market. So you can talk yourself into low SIL for rare events, but it has a way of catching up with your company if you do that. Let's switch to cybersecurity, the second out of the 4 core areas. Cybersecurity has to do with protecting your system from losses caused by malicious actors. The security properties vary by application. In the information technology world, in the normal everyday enterprise computing world, We tend to care about confidentiality a lot. We're worried about people stealing your password, stealing your credit card, and so on. And encryption is the typical technology used for that. But in the embodied AI world, if you have a robotaxi, while privacy does matter, everyone can see the car on the road, everyone can see you turn left, you turn right. So the confidentiality is less of an issue, and more of an issue is integrity and availability. You want to make sure that no one has modified the software to make it unsafe, and you want to make sure that the safety functions associated with mitigating risk remain available so that you don't have a loss of safety. There's an emphasis on safety, integrity, and availability rather than confidentiality. If somebody says their embodied AI system is safe because they use encryption, ask them about integrity and availability, because encryption helps with confidentiality, but not necessarily with other properties. One useful way to look at security attacks for embodied AI systems is that they're malicious faults. If you care about safety, cybersecurity attacks are a way that faults can occur that you thought probably wouldn't happen if you were just thinking about safety. For example, an attacker might introduce a fault missing from the hazard analysis, or they might violate a safety analysis assumption. You may have said a particular hazard is extremely rare, so you're not going to worry about it. Well, then the attacker's job is to find a way to make that hazard happen frequently instead of rarely, and therefore induce a safety problem into your system. A big problem with embodied AI systems in particular is that the attacker often has physical access to your system. If you have a server in a locked machine room in the middle of nowhere, it's going to be hard to get into it and modify the hardware or software physically. But if you have a car parked on the street, or you have something attached to a utility pole, it's going to be easy for an attacker to gain physical access to it and potentially modify it. So that makes security challenges a lot more difficult when you're talking about embodied AI safety. The third area to have literacy in is machine learning. Now, this talk is not going to spend an hour explaining machine learning. This is a very simplified version, but it includes the concepts that matter the most when we're talking about safety. Machine learning, in a nutshell, is you first feed a system a lot of data. We don't necessarily know how to write a particular software function by writing source code, so instead we say, well, we're just going to train it up on a bunch of data. We're going to show it a bunch of examples and let the machine learning figure out what the right behavior is. So it learns statistical properties. This is an important point. Machine learning does not learn the way a person learns. They don't learn to reason. It doesn't learn to think through. It doesn't learn to build internal physics-based models, at least with typical machine learning. Rather, it learns statistical properties. You can show machine learning a bunch of people's faces, and it does not say, oh, I know what a nose is, I know what a chin is, I know what an ear is, but rather it builds up statistical relationships that says, well, that image is statistically similar with a bunch of features to things that I've been told are a face, so it must be a face. And it generates statistically plausible results. There are different flavors of machine learning. One of them is classification. Is it a car? Is it a person? There's a family movie called Mitchells versus the Machines where the family dog, who's obviously sort of a weirdly animated dog, is it a dog? Is it a pig? And the machines all decide it's a loaf of bread as a plot device. Now, what's important here, they're not saying it's really a loaf of bread. Obviously, it's not a loaf of bread. What this classification is saying is that image is statistically more similar to a loaf of bread than to a dog or a pig. So when a machine learning system sees a human face or sees a particular person, it does not know that's a person. It doesn't know what a person is. What it's saying when it says, oh, that's a person, is that thing I'm looking at is statistically more similar to people that I've been trained on than other things I've been trained on. And that's an important difference. There's also generative art where you can take a random set of noise and you can say, well, how much catness is in there and how much Picasso-ness is in this picture? And then you can randomly perturb it and say, well, that version has a little more cat in it, a little more Picasso in it. And if you do that enough times in a row, you end up with a picture that looks kind of like a cat drawn as if it were drawn by Picasso, even though it's a completely synthetic image. Obviously, that's a simplified example, but the idea is you can generate things that statistically are similar to the thing you wanted, even though it's not an authentic image of anything in the real world. A third flavor of machine learning is large language models or foundation models, which predict the next likely output in a sequence. You can say it was a dark and stormy And the most likely word in the English turns out to be the word night. It was a dark and stormy night, but it could be other words. And it's a little more sophisticated than that. It has tremendous ability to take context, sometimes of tens of thousands of surrounding words. And so what it produces is very sophisticated mimicry of things like language in LLMs, or things like what's the next picture in a video of a car driving down the road as seen from the driver in a vision-based foundation model. All three of these things can produce really impressive results. They're statistically very sophisticated, amazingly capable systems. But they're not artificial general intelligence. They don't actually think the way people think. And I understand this point is contested, but where I'm coming from, they don't think the way people think. They don't reason the way people reason, even though they say they're reasoning. That's not what's going on. They are statistical models. And so the important thing is, it's a mistake to attribute to them thinking. Rather, they're statistical mechanisms that can do really impressive, capable things, but don't go too far and don't assign them agency and don't assign them thinking. There's a famous test called the Turing test, in which if you're chatting with something over a typewriter keyboard and display, you can decide whether or not you think the thing on the other side is a machine or a person. And if it's a machine that convinces you it's a person, it passes the Turing test. But the thing is, we've known since a project called ELIZA back in the 1970s that some people are very susceptible to believing something's a person when it's really a machine. And it turns out that the Turing test is more of a measure of gullibility of the person on the other end of the keyboard than it is as to whether the machine has real intelligence or is just really good at faking it. An important consideration when using machine learning in embodied AI is that machine learning breaks the V model. So let's go into some detail on that. The V model is a process model that's baked into a typical safety standard, saying that the way you develop systems is you start with a concept of operations, and then you break that down into requirements and architecture, detailed design, implementation, and so on. And you go down the left-hand side of the V, starting with a high-level idea of what you're building, and then refining it down to implementation. An important thing here is you're tracing down the left-hand side. The requirements match the concept of operations, the detailed design matches the requirements, the implementation matches the detailed design. So you have a really strong belief that as you go down the left-hand side, the implementation actually builds the thing that you wanted to build. The other half of the V on the right-hand side is the validation, where you say, well, we're going to do a test to make sure the requirements are all there. We're going to make a test to make sure the implementation matches the detailed design, and so on. So you have verification going up and down the left side and validation going across the right and left. And if you do this according to a safety standard, you have a pretty good expectation that you have a safe outcome. An important thing to keep in mind, though, is that testing is not there to prove safety. Brute force testing never proved safety of any complex system. That's not how it works. What's really going on is the left-hand side is applying engineering rigor. And so the more risk there is and the more safety integrity you need, the more engineering rigor you apply. The left-hand side is applying engineering rigor to set a prior expectation of safety. You're saying, I did all these engineering activities on the left, so I'm pretty sure it's safe on the right. And what I'm doing on the right is not testing to see if it works. I'm testing to make sure there's no gaps in my engineering rigor. I'm testing to make sure that all the things that I thought I did, I actually got right. So the testing is not there to prove it's working. It's not there to prove it's safe by just testing alone, but rather it's there to validate that the engineering process was executed properly. And here's the problem with machine learning. Machine learning breaks the V. Think about it. If you have a set of requirements, well, a car has to drive down the road and it can't hit things. And then you use machine learning by saying, well, let's just train on a bunch of driving data. Well, what did that driving data have to do with the requirements? Kind of nothing. You've broken the chain on the left. And that means on the right, you have to do brute force testing of everything, which you can't do. It's impossible to do enough testing to prove safety. What's the fix for this? Well, the fix is to somehow stitch together the upper left of the V with the machine learning. For example, you define a bunch of scenarios and then you train on those specific scenarios. Well, that's no longer just machine learning brute force training. That's trying to come up with an expectation of safety by stitching together the requirements of the machine learning. So you can, in principle, do safety with machine learning, but it requires more than just training on a bunch of data. You you have to have a story to tell about why you think the safety was there and why the testing is proving the safety is there, as opposed to just testing the machine learning to see what happens. The fourth core area of embodied AI safety is understanding humans and how they interact with machine learning and safety critical systems. There are two important principles here. The first is that humans have a perception response time. Humans cannot react instantly. You might think, well, they can react in a fraction of a second or a second, but it actually takes longer than that. People have to see something happen. They have to figure out, what the heck am I looking at? They have to formulate a response, and then they have to initiate the response. That's perception response time. Now, some responses you can make very, very quick. People sometimes call it muscle memory. But when you have a complex situation, it can take a long time to process it. Ones of seconds, fives of seconds, tens of seconds, depending on what's going on. So that's one thing to remember. It's not instant to respond. It always takes some time to respond. The second thing is a concept called the ironies of automation. The idea is that you have automation complacency and automation bias. Automation complacency is if you're used to a computer-controlled system working really well, then it's really hard to keep paying attention. The other problem is there's a thing called automation bias, which is when presented with a human-generated output and a computer-generated output, people tend to trust the computer regardless of what's really going on. They just overtrust computers. So you add these together, people tend to get complacent and overtrust computers, especially if they've behaved well for a while. And that trust lengthens the perception response time. The more you trust it, the harder it is to react quickly when something goes wrong. So now let's have a plan where we're going to have computers that work almost all the time, but not quite all the time. And we're going to tell people that they have to intervene when something goes wrong. Well, they have limits to how fast they can do it, and it's pretty much guaranteed that the better the system is, the longer it will take them to respond because they're just not expecting it. So the irony here is that the more effective the automation is, the more ineffective human safety supervision will be. So when you hear people being shamed for checking their cell phone while a computer is driving the car down the road, I'm going to say they shouldn't do that for sure. It's the wrong thing to do. But it's basically inevitable. This is what people do. This is how people behave. And so having trouble supervising a really boring automation task is baked into human nature. You can say there's a lack of moral fiber for people who can't pay attention, but really what you're asking them to do is to be superhuman. Yes, you should put down the cell phone, absolutely. But expecting that no one will ever check their cell phone when they go hours and hours watching boring automation that almost never tries to kill them is asking a whole lot. You're not going to get safety that way. This brings about some serious ethical and legal issues. Who's responsible for embodied AI misbehavior, whether it's a car or a drone or a factory control plant or a medical device? If the embodied AI system misbehaves and there was a human who was supposed to intervene, but we know people are bad at intervening when things almost always work correctly, who exactly is responsible? Should we always blame the human, or should the manufacturer have some responsibility for building a system that is easy to supervise and does not make mistakes that are hard for people to correct for? Moreover, blaming the human for not reacting instantly is not going to make it safe. You can set up the human and say, well, it's the human's fault. Our plan is to blame the human. There's a name for that. It's called the moral crumple zone. Hey, we're going to build a system that will make mistakes, and our plan is to blame the human to protect the system. You can do that, and you might succeed legally, but you're not going to be building a safe system that way because people have a non-zero PRT that gets longer the better the automation is. So you have to have a plan for how you're going to deal with the fact that your automation will make mistakes and people will take a long time and not be perfect at catching them. What's your story for how the net combination of the computer and the person will actually be acceptably safe in the end? Now that we've looked at the four core areas, let's talk about embodied AI safety issues in the wild. There have been robotaxis in San Francisco and now other cities for quite a while now, and we've seen some repeated patterns of problems, and we can learn from them. Just because you're not building robotaxis does not mean you should ignore the lessons that these have to offer. The first one is that false alarms are an issue. In robotaxis and generally cars, there's a thing called phantom braking. That's where the car brakes for no reason whatsoever that's apparent to people in the car or people around the car. It just gets a false detection of some obstacle and it slams on the brakes, and sometimes people run into it from behind because they were following what you could say in retrospect was too closely. The driver in the car, is, if there is one, cannot probably react in time because of their perception response time, and so they can't keep it from stopping because by the time they react, the car's already stopped enough, it's been hit from behind. False alarms are a problem, and they're a little bit tricky because it's very easy to blame other folks in the environment for not giving the system enough slack for false alarms. But they're acting differently than other actors in the environment. So a robotaxi that jams on its brakes with high force all the time will cause a higher crash rate, even though it might be able to blame everyone else for the crashes. But a crash is a crash, and if you have a higher crash rate, that's an issue. So dealing with high false alarm rates is a potential issue for any embodied AI system. What's your plan for that? The next one is unpredictability. Safety critical systems are designed to be repeatable. Highly deterministic is the word you often hear. And the idea is if you run a test once, you'll get the same test result as running it the next 100 times, which makes it easy when you're executing an engineering process to say, well, pass the test, so we're done. But embodied AI technology is inherently non-repeatable. It will often behave differently in what appeared to everyone observing to be identical circumstances. So how many times do you have to test it to know it passed the test? If it passes the test once, was that because it got lucky? Or is it going to pass the next 1,000 times? And what if time number 1,001 is the time it fails? That gets to be a big problem when safety is determined by things that are down in the 1 in a million, 1 in 100 million type of situation. Do you really need to have to run 100 million tests on every possible capability? Well, you can't afford to do that. So dealing with unpredictability is an issue. Machine learning can be really awesome at stuff where 90%, 99% accuracy is what you need. If you're trying to do movie prediction, I think you'll enjoy this movie. 95%, 99% is awesome. That's because the cost of a misprediction is pretty low. But safety is all about a bunch of nines, 1 per 100 million, 1 per billion, numbers like this. And trying to apply statistical approaches to get that many nines of availability or dependability or correctness is really hard. Statistics just aren't really good at that. And that mismatch gets to be a problem. And now we're back to safety being determined predominantly by the rare high severity events. So how do you deal with that? Along with that, machine learning has a problem with heavy tail edge cases. So this is a picture of a cow falling off a cliff. I've driven down a road where cows actually do fall off the cliff. That's a thing. It doesn't happen often, but if it happens when you happen to be there, that's a problem. And for machine learning based robotaxis and the like, have they been trained on that sign? How many in the audience have actually seen one of those signs in the real world as opposed to just in a cartoon? There are an almost infinite number of rare events that could be high severity. And if you're using machine learning, you only know how to work on things you've been trained on. And what about all the stuff you didn't think of? What about all the stuff you haven't seen yet? How do you respond to a novel, potentially high-risk situation? That's been a challenge, and it's going to keep being a challenge because the world is full of novel situations. What we should do, instead of saying, well, we'll be complete, we'll find them all, that's never going to happen. And even if it does happen, the world will change tomorrow and you'll be out of date. So if you want to do safety for embodied AI, you just have to acknowledge you will have incomplete training. You need to be acceptably safe. I didn't say perfect. Acceptably safe, even though you have incomplete training. You need a story for that. And in practice, for the foreseeable future, any embodied AI system also needs a human backup. So it's not that you have to be perfect and handle everything. It's that you have to, part one, handle almost everything, and part two, have a system that knows when it's encountering something novel and falls back to a human. Maybe it doesn't keep operating, maybe it does a safety shutdown and calls the human and says, hey, I need help, I don't know how to handle this. Those are things you have to get right, and if you get them wrong, it can be a big problem for you. Something that became evident with robotaxi operation in San Francisco is that safety is more than just net harm. People want to say, well, safety is the number of people you've injured or the number of people you killed and maybe the number of crashes. But there are a lot of things relevant to safety that don't involve an actual crash that causes vehicle damage. Here's one example of a robotaxi and another robotaxi following it. And if you look closely, there's a yellow ribbon hanging off the top of the car. What's happened is it's run through a downed power line from the municipal transportation system, and it's dragging some warning tape, police scene tape, do not enter. It just drove right through, dragging the tape, dragging the wire behind it. And it's a good thing there was no passenger in there, and it's also a good thing that wire did not happen to be electrified at the time. Was that safe? Well, nobody was harmed that time, but it doesn't feel safe. Another example is a robotaxi going into a construction zone. So you can see a flag person, and the signs there say do not enter, road closed, but there was a lane open probably for construction vehicles. And for whatever reason, the robotaxi decided to dive through that lane and just drive into the construction zone. There's plenty of videos of robotaxis encountering problems in construction zones. And again, nobody was hit, nobody was killed, no one was injured, there was no actual crash, but that does not exactly scream safety. And so one of the questions to ask is, if nobody was harmed this time, does that make it safe? And I'm going to say no, because these introduced risky situations and getting lucky is not the same as getting safe. Nobody was harmed this time, but it was just a matter of luck. An overarching problem we've seen with safety is that safe enough has to include avoiding risk hotspots. A common talking point for safety for an embodied AI system is you say, well, it's safer than a human operator. And so our car driver is safer than a human driver because human drivers have these problematic behaviors. Maybe our aircraft pilot will be safer than a human pilot who makes mistakes. Maybe we'll have better outcomes than a radiologist reading medical imagery because the machine doesn't get tired and doesn't make mistakes, and so on. And so people say, well, we want to look at the net outcomes, and if the net outcomes are safer, then it's a safer system. And there's certainly an appeal to this. Now I'm going to give some very hypothetical examples, and I stress the hypothetical to make the point. If you say, well, on US roads, there are about 40,000 people killed every year, and if computer drivers were 100% of the cars and they reduced it from 40,000 to 10,000, boy, that'd be a win, because 30,000 fewer people ever dying. And there's a compelling logic to that argument. But in practice, we're probably not going to see 3-to-1, 5-to-1, 10-to-1 changes. We're going to see, at least at first, very small changes for a number of reasons. And we're also going to see there's more to it than just the numbers. You can say, sure, this computer driver is 10% safer than a human driver, but there are other types of risks that are going to be unacceptable. And so here's some examples of risks. What if there's specific unsafe behaviors? What if robotaxis keep having crashes into emergency vehicles at accident scenes and hurt emergency responders? What if they transfer risk onto the vulnerable? What if the number of fatalities cuts in half, but all of the fatalities are pedestrians? So no one inside a robotaxi ever dies, but the number of pedestrian fatalities triples or quadruples. And now what you have is lots of pedestrians dying, but the people in the robotaxis are safe. I'm going to say that will be a socially problematic situation, even though the total number of fatalities went down. What if there's harm due to embodied AI negligence? What if every single mishap that results in a death or an injury comes when the embodied AI system breaks the law? What if every single fatality involves running through a red light and hitting a pedestrian? That's not going to be okay. What if there are negative externalities? One example we saw in San Francisco was robotaxis parking in firehouse driveways so the fire trucks couldn't get out in case of an emergency. Now, no one ever pinned down a fatality or an injury due to that, but it's a problem. They can say, well, the robotaxi was just being safe. It was doing a safety shutdown. Yeah, I get that, but a human driver would be very hard pressed to justify parking in a firehouse driveway, but the robotaxis were doing that more than once. What about compensating for other mistakes? You can say, well, our embodied AI system behaved in a way that was according to the law. It wasn't negligent, but somebody else made a mistake and we failed to prevent it. A crash is a crash, and if you fail to avoid a crash, you might have a higher mishap rate, even though it's never your fault. And there's also personal and psychological safety. What if a robotaxi dumps a rider out in a really bad neighborhood at 2 a.m. instead of delivering them to their spot? There was no crash, the person wasn't harmed in a mishap, but that still could result in issues for that person. This list of things other than net safety that do matter for safety changes how you have to look at safety. And when there's a human operator present, you can say the human operator is responsible for all these kind of risks, for avoiding these risks. But once you take the human operator out, which is usually the goal of embodied AI, is to get rid of the human operator or to greatly reduce their responsibilities, someone has to take care of these higher level safety concerns. To do that, you need to do more than say we're looking at the net losses. You need to actually identify various stakeholders have risk hotspots they're in charge of. The fire department says you're not allowed to block fire trucks, and I don't care if it's hard to prove anyone died from that, you're still not allowed to do it. And so a single risk metric of fewer fatalities or fewer injuries is not going to be enough. Instead, there are a bunch of constraints on acceptable behavior, and those constraints exist whether or not they are reflected in the net loss rate. You have to obey all the restrictions, all the constraints, and once you're done, then you can optimize whatever you want. One of those constraints is very likely to be fewer fatalities and probably fewer injuries, but it's not the only constraint. This is a fundamental rethink of how we have to look at safety once the human operator is taken out of the loop. A topic I want to cover very specifically is the concept of negligence. This is a legal topic. I'm not a lawyer, but I'd like to give a layperson understanding of what negligence is and how it affects embodied AI safety. There's the concept of a duty of care. If you're a human operator, whether you're driving a car, operating a piece of machinery, or performing a service, you have a duty for the safety of others if you're doing something potentially dangerous. And the question is whether you're acting reasonably. There's the idea of a reasonable person. So a reasonable person would try and obey the law. They would try to do things that do not put other people at undue risk. They would try and follow procedures. And ultimately, in the jury system, a jury sits down and decides, well, was that reasonable behavior? Did they make avoidable mistakes? Did they follow procedures? Things like this. And the requirement is, if you're going to do something potentially dangerous, you don't have to be perfect, but you should act as a reasonable person would to safeguard the safety of others when you're doing this activity. If you breach that duty of care by failing to act as a reasonable person would, and that results in harm to someone else, then you have a situation of negligence. So when you hear about tort law negligence lawsuits, wrongful death, wrongful injury, something like that, this is the area of law we're talking about. And the idea is that if someone acts unreasonably and it results in harm to someone else, then that person who is harmed can seek compensation. Right now, there is no established legal duty of care for computers. So if a computer is driving a car or a computer is flying an airplane, there is no duty of care under tort negligence law for them to act in a reasonable way. That needs to change. Now, the important thing here is duty of care is not based on design defects. That's a different theory. It's based on behaviors. So right now, if a computer in a robotaxi causes a loss, you have to go after a product liability saying there's a design defect. But the way this technology works, it may be extremely expensive to prove a design defect, and there may not actually be a design defect. It might just be, well, machine learning is not perfect. Every once in a while it makes a mistake, and the designer did the best they could, and there's no cost-effective alternative, and they warned everyone, and so on. There's a list of things you have to do for product liability. You might find out that an embodied AI system is not defective according to product liability law, but still results in losses. If we try and make every lawsuit a product liability lawsuit, it will break the legal system. They're extremely complex, they're expensive to run, and they should be unnecessary. If a robotaxi runs a red light and hits someone, why do we need to do reverse engineering to prove where the design defect was? We should just say, look, it ran a red light. If a person ran the red light, we'd say they were negligent, assuming there's no extenuating circumstance. We should treat the computer driver the same way. So what we really need to do to make this technology viable at scale is adopt a duty of care for computers so that if an embodied AI system has a dangerous behavior that results in harm, that we can use the same rules we would use as if a human were operating it. But computers aren't people, they don't run property, they can't go to jail. So we should make the manufacturer the responsibility party. Why the manufacturer? Well, that's whoever it is that had the ability to decide whether the machine was going to operate safely or not. A key attribute of negligence is that statistical safety does not forgive negligence. And let me give a completely hypothetical example. Let's say that a human driver drives 1 billion miles with a bee, which is more than any person could really drive. They drive 1 billion miles with a bee, and in the US they would have expected to have 10 fatalities. But they don't have any. They have no fatalities at all. And then one night they're in a hurry, they run through a red light because they think there's nothing going on, and there's a pedestrian, and tragically they hit and killed a pedestrian. If they show up in court under negligence, they're not allowed to argue, well, I've gone 1 billion miles, I should have killed 10 people by now, I haven't killed anyone, so this one should not count. I should get it for free. No one would take that kind of argument seriously. But let me contrast that to a robotaxi argument where people say, well, our robotaxis have had 1 fatality in 1 billion miles, and yeah, that 1 fatality was due to running a red light hitting a pedestrian, but we've saved 9 people, so it should be okay, there should be no penalty. Well, if it's not okay for a human, it should also not be okay for a robotaxi. Negligence laws are going to have to apply to embedded AI systems in a way comparable to people, or it's going to break the legal system. The robotaxi industry has had some misguided messaging, and this is a cautionary tale for anyone who's building embodied AI systems who wants this on safety. They've been saying for years, we're going to save lives. Human drivers are so terrible. Here's a full-page ad that was taken out in the New York Times. Human drivers are terrible, and the intended message is pretty obviously, but our robotaxis don't drive drunk and they don't drive distracted, so we're going to be safe and we're going to save all these lives. And we found out that robotaxis actually do make mistakes, including from the same company. The problem with we're saving lives as a message is it's all downside. Proving saving lives requires probably 10 fatalities worth of miles, so we're back up to 1 billion miles. And during those 1 billion miles, you're going to have hundreds, if not thousands, if not more, embarrassing moments captured on pictures. And you've seen a couple of them in this talk already. Popular opinion is not going to last 1 billion miles saying, well, yeah, we saw a robotaxi hit a telephone pole, but they're saving lives. When will we know that? Oh, wait a few years and we'll then be able to prove they're saving lives. Or that robotaxi hit a bus, or that one got stuck in wet concrete, and so on. The problem is that every negative picture that shows a robotaxi doing something that people think would be a bad human driver undermines the credibility of robotaxis, and meanwhile you're waiting years to save lives. People think in stories, not statistics. Now let me bring that home. People think in stories, not statistics. When you saw these pictures early in this talk, did you say, oh, those pictures prove it's a safe driver? More likely your reaction was, well, if that had been a human driver, they would have been a bad driver. So why would you not conclude the computer drivers are bad? Now, I didn't say they're bad. I asked why you would conclude they weren't bad. And the catch here is a picture of a crash is a very compelling story. And some abstract understanding of both of these companies at the time of those crashes said, oh, our cars are multiple times safer than people because we're having so many fewer crashes. But that didn't stop people from seeing these stories. Right now, one study shows that 61% of US drivers fear robotaxis. Most of them have never seen a robotaxi. Fewer have even been in a robotaxi, but they're all seeing these pictures. So think about when you're saying, well, we're going to save lives, and meanwhile all these crashes happen, to your application, whether it's robotaxi or something else. Every adverse event is going to make news, and you need a story that is not, well, someday it'll save lives, so ignore all the mess. That's not going to work out for you. Taking all this into account, I think we need to reimagine safety engineering. There's some issues that we have to address at the high level. One is societal. Net risk is not going to be enough. There's more aspects to risk than just the total mishap rate and the total fatality and harm rate. And what we're going to find out in real life is that better per human will be per incident. Every single time there's a high visibility loss event, people will judge the embodied AI system on whether they, as an operator or a reasonable operator, would have avoided that mishap. And if the answer is, oh, I would never have made that mistake, whether it's true or not, if they think it's true, that will prove to them as a person that the technology is unsafe. So selling on net risk is not enough. You're going to be judged on every single incident, and you have to have a plan for dealing with that. You're not going to be perfect, but you need to have a plan for how you plan to deal with that. The next thing is there's a technical challenge, heavy tail edge cases, Rare events with high severity, there's going to be a lot of them. So many you can't just say, well, collect the ball and it'll be fine. You're going to have to plan for incomplete training. I look at it as you have an imperfect system operating in an imperfect world, and yet it's going to happen. The next one is there needs to be an accountability approach. So here's a picture of a drone. And this drone, you might say, all right, go take a picture of this building over here. And the building happens to be on the other side of an airport. So the drone takes a shortcut over the airport and puts a flight in risk. There's an aircraft landing and there's a near collision or maybe an actual collision with an aircraft. Who's accountable for that? Is it the person that said take a picture and thought that, of course, the drone will out-navigate around the airport because that's what it's supposed to do? Is it the programmer who told the drone to navigate? What if the drone was just trained and it's never done that before? It just decided this particular day it's going to fly over an airport. How does that work? Well, we're going to have to apply human negligence standards to AI-based systems. There's no other system that's going to be viable. We're going to have to say, well, if an AI system misbehaves, whoever had the ability to overrule the misbehavior is responsible, and probably that's the manufacturer. We also have to respect the limits of human capabilities. Humans have limits in perception response time, they have limits in automation bias and automation complacency. If the person operating that drone had photographed 100 houses on the other side of the airport, and every time it had gone around the airport, it's kind of unreasonable to expect them to monitor every second of flight this time, because they know in their heart it's going to work, but this is the time it does something dangerous. From a safety point of view, it's no longer enough to say safety is just the minimization of risk as a single metric. There needs to be a multi-constraint satisfaction approach. There are going to be a bunch of stakeholders who put constraints on how the embodied AI system is allowed to behave. Some of them will have to do with net risk outcomes, but some of them will be rules that really have nothing to do with easy to understand net risk, but rather non-interference with operations, such as not messing with aircraft flight paths, and other rules that are in place for things that are indirectly or maybe even not at all related to mishaps caused directly by this embodied AI system. Stakeholders are going to have to contribute aspects of risk constraints to the requirements, and the safety evaluation is going to have to make sure all the constraints are met rather than just saying, well, we've minimized the risks we know about, so it's good enough. For this technology to succeed at scale, we're going to need justifiable trust for safe embodied AI. That means going beyond promising we're going to save lives to measurable, responsible behaviors that can be measured and understood by the general public in the near term to build trust, not that hopefully someday they do save lives, but set that aside because it'll take too long to understand. We need to build trust with positive interactions in the near term, and the outcome needs to be as much or even more so that the company deploying the embodied AI is a trustworthy company. And then there's some credibility that someday it'll save lives, but at least we know in the near term they're going to be trustworthy. There has to be accountability. Companies building and deploying embodied AI systems have to accept proportionate responsibility. If there's some sort of loss event, they shouldn't say, well, let's find someone else to blame, it can't be our fault. Much more, it should be, well, we have independent oversight. A bad thing happened, we've done our best, we follow all the standards, we've done our best to try and avoid it. We were surprised, but we're reacting by finding it, fixing it, and here's the independent oversight, and here's the evidence that we have fixed it this time, and you should now trust us that we're a good actor, as opposed to we're going to save lives sometimes, so forgive the mess as we go. And finally, we need a safety constraint satisfaction approach. Net risk reduction is not going to be enough for safety. Safety got a whole lot more complex when we removed the human operator, who used to be in charge of a lot of the subtle and difficult to quantify aspects of safety. Now the embodied AI system has to do it all, and it needs to be a lot more sophisticated in its understanding of safety to do that. This talk is based on a book on embodied AI safety that I wrote, and there are also 2 other books in the series, one on how safe is safe enough from 2022, and another one is the UL 4600 guidebook, where UL 4600 is a safety standard specifically for autonomous systems.